Welcome to the lesson on lithium-ion battery, abbreviated as Li-ion battery. In this lesson, we will look at the history, chemistry, and construction of lithium-ion batteries. Let us look at our lesson objectives. By the end of this lesson, you will be able to explain the basic working principle of lithium-ion batteries. Next, you will be able to identify the key components of a lithium-ion cell. Then, you will be able to compare the construction, advantages, and limitations of cylindrical, prismatic, and pouch lithium-ion cell designs. Following that, you will be able to explain the factors influencing battery performance. Finally, you will be able to describe the overall benefits and potential safety concerns associated with lithium-ion battery technology in BEVs. A lithium-ion battery is a rechargeable battery that uses lithium ions moving between electrodes to store and deliver energy. Unlike older BEVs that might have used nickel metal hydride batteries, lithium-ion is the dominant battery technology in modern BEVs. Let us now look at the discovery of lithium. In 1817, Swedish chemist Johan Arfvedson identified lithium as a new element and named it based on the Greek word lithos, meaning stone. This discovery paved the way for future advancements in lithium-ion battery technology. Lithium-ion batteries reign supreme in transportation due to their high voltage, superior energy storage capacity, long charge holding ability, and lack of memory effect. The positive electrode is lithium cobalt oxide. The negative electrode is a specialty carbon. Electrolytes are lithium salts. Lithium salts dissolved in a solvent enable the movement of lithium ions. Differing lithium technologies are being considered and used due to the availability of minerals. During operation, lithium ions travel between the positive and negative electrodes, meaning that during discharge, lithium ions travel from the negative electrode to the positive electrode and vice versa during charging. Lithium-ion batteries comprise several smaller units called cells. Each cell contains three essential components: a positive electrode, a negative electrode, and an electrolyte. The positive electrode is typically composed of lithium metal oxide, while the negative electrode is usually made from carbon, such as graphite. During charging, the lithium ions move from the positive to the negative electrode through the electrolyte. This is an oxidation reaction, which means the lithium ions lose electrons. The electrons flow through the external circuit to the positive electrode, which charges the battery. During discharging, the lithium ions move from the negative to the positive electrode through the electrolyte. This is a reduction reaction, which means that the lithium ions gain electrons. The electrons flow through the external circuit to the negative electrode, powering the drive motor. The positive and negative electrodes are separated by a separator, which is a thin, porous material that allows the lithium ions to pass through but not the electrons. The separator prevents the electrodes from short-circuiting. The key here is that the flow of electrons is essentially electricity. So, when a BEV is being driven, it uses the stored chemical energy in the battery and converts it into electrical energy. This electrical energy gets converted to mechanical energy by the electric motor to move the car. Presently, there are three main types of lithium-ion battery designs. They are cylindrical, prismatic, and pouch cells. Overall, cylindrical cells are often chosen for their robust thermal management, mechanical stability, lower cost, mature manufacturing processes, and modularity. However, the choice between cylindrical, prismatic cells, or pouch cells ultimately depends on the specific requirements of the BEV, including factors like energy density, design constraints, and cost targets. Note that there are new technologies being developed for future types of cells. As we proceed, we will learn more about each of these cells. The cylindrical battery design shape resembles a traditional D cell with a steel can. The prismatic battery design shape resembles a rectangular or box-like design. The pouch battery design is a flat rectangular shape. This shape is distinct from cylindrical or prismatic cells, which have a more rigid and defined structure. For the construction of the cylindrical shape, the active materials are processed into long ribbons and wound in a spiral inside the cylindrical case. Let us firstly look at cylindrical cells. These cells offer a compelling combination of performance, safety, manufacturing efficiency, and reliability, making them a popular choice for battery electric vehicles, BEVs. However, the optimal cell type ultimately depends on the specific requirements of the vehicle and its intended use. Let us look at the performance and safety of cylindrical cells. Superior thermal management. Cylindrical cells have a higher surface area compared to pouch and prismatic cells. This allows better heat dissipation, which is crucial for maintaining the battery's performance and safety. Cylindrical cells, due to their structure, are less prone to thermal runaway, a condition where a battery cell overheats and causes neighboring cells to overheat, potentially causing a fire. Enhanced mechanical stability. The cylindrical shape provides a strong structure that is more resistant to physical impacts and vibrations. Mechanical stability is important in automotive applications where the battery pack is subjected to constant vibrations and possible collisions. Next, we will look at the manufacturing efficiency and the cost of cylindrical cells. Mature manufacturing processes. The production lines for cylindrical cells are well developed, automated, and honed for large-scale manufacturing, allowing lower costs and consistent quality. Scalability and modular design. Their modular structure simplifies pack design and assembly, allowing for flexible battery configurations. Lower production costs. Cylindrical cells generally have lower manufacturing costs due to their scalability, mature processes, and less stringent tolerances. Cylindrical cells are widely available as they have been mass-produced for many years for various applications, providing a reliable and cost-effective supply chain. Now, we will look at the longevity and reliability of cylindrical cells. Longer cycle life. Cylindrical cells exhibit a longer cycle life due to their resistance to swelling and degradation, making them suitable for BEVs requiring extended battery lifespan. Consistent performance. Their uniform current distribution and reduced risk of mechanical stress contribute to consistent performance over time. While cylindrical cells offer several advantages, there are certain factors to consider. Let us look at some of them. Energy density. Compared to pouch or prismatic cells, cylindrical cells may have lower energy density, which can limit driving range. Space constraints. The cylindrical shape can make it more challenging to pack cells tightly together in a limited space, potentially reducing the overall energy capacity of the battery pack. Mechanical stress. Cylindrical cells can be subjected to mechanical stress during charging and discharging, which can lead to degradation over time. Thermal management. While cylindrical cells generally have good thermal management properties, they may still require careful cooling systems to prevent overheating and ensure optimal performance. It's important to note that these considerations can be mitigated through advancements in cell design, materials, and battery management systems. However, the choice between cylindrical, pouch, or prismatic cells ultimately depends on the specific design requirements of the BEV and the desired balance of performance, safety, and cost. For the construction of the prismatic shape, the active materials are fabricated into flat plates, just like those of a conventional lead-acid battery. Let us now look at the construction of prismatic cells. These cells are another major type of lithium-ion battery design, characterized by their rectangular or prismatic shape. They are a compelling alternative to cylindrical cells, particularly for applications where high energy density and flexible pack design are paramount. Now, let's look at the high energy density of prismatic cells. Prismatic cells can offer higher energy density compared to cylindrical cells, leading to a longer driving range. Next, let's look at the flexible design. The flat shape of the prismatic cells allows for more flexible pack designs, potentially enabling larger battery packs within a given space. Now, we will look at the reduced internal resistance. Prismatic cells generally have lower internal resistance, which can improve charging efficiency and power delivery. Prismatic cells offer a compelling alternative to cylindrical cells, particularly for applications where high energy density and flexible pack design are paramount. However, their thermal management challenges and manufacturing complexities need to be carefully addressed to ensure optimal performance and safety. Thermal management. While prismatic cells can be designed for effective thermal management, it can be more challenging due to their larger size and potential for uneven heat distribution. Manufacturing complexity. The manufacturing process for prismatic cells can be more complex and less automated compared to cylindrical cells, potentially leading to higher costs. Mechanical stability. Prismatic cells may be less mechanically robust than cylindrical cells, especially when subjected to impacts or vibrations. For the construction of the pouch cells, a negative electrode, a positive electrode, a separator, and an aluminum laminated film are layered together with a positive tab and a negative tab connected to the electrodes. Prismatic cells are another major type of lithium-ion battery design, characterized by their rectangular or prismatic shape. They are a compelling alternative to cylindrical cells, particularly for applications where high energy density and flexible pack design are paramount. Let's look at the laminated structure of pouch cells. Pouch cells typically consist of a laminated structure, combining a cathode, an anode, a separator, and an electrolyte within a sealed pouch. Next, we will look at the flexible shape of pouch cells. The pouch shape allows for greater flexibility in battery pack design, enabling various form factors and configurations. Let's look at the thin profile of pouch cells. Pouch cells can be made relatively thin, allowing for a more compact battery pack. Overall, pouch cells are a popular choice for various applications, including consumer electronics, battery electric vehicles, BEVs, and energy storage systems, due to their combination of energy density, flexibility, and cost-effectiveness. However, pouch cells also have some limitations. Structural integrity. The pouch cells might be less durable than cylindrical cells, making them more susceptible to damage from external forces. Thermal management. Managing heat dissipation can be more challenging in pouch cells, as uneven heat distribution can lead to safety concerns. Let us now look at the main differences among these three main types of cells. Cylindrical cells are often chosen for their high power density, making them suitable for applications that require rapid acceleration and high peak power. This makes them a popular choice for BEVs that prioritize performance and quick response times. Prismatic cells are known for their higher energy density, which translates to longer driving range. This makes them an attractive option for BEVs that need to travel long distances on a single charge. Pouch cells offer a more flexible design, allowing for various pack configurations and shapes. This makes them suitable for applications where space is limited or unique battery pack designs are required. Let us now look at another battery type, which is lithium polymer. These batteries are less common in mainstream BEVs compared to cylindrical or prismatic lithium-ion batteries. Lightweight and flexible, their polymer electrolyte allows for a thinner, more flexible design compared to liquid-based batteries, potentially saving space and weight in BEV battery packs. High energy density. LiPo batteries can achieve high energy density, which can contribute to a longer driving range. Customizable shape. Their flexible packaging enables them to be designed in various shapes and sizes, potentially allowing for more innovative battery pack designs. Lithium polymer LiPo batteries have some limitations. They are higher cost, swelling, thermal management, and mechanical stability. Higher cost. The manufacturing process for LiPo batteries can be more complex and expensive compared to traditional lithium-ion batteries. Swelling. LiPo batteries can swell or expand over time, potentially affecting their performance and lifespan. Thermal management. Managing heat dissipation can be more challenging in LiPo batteries, as uneven heat distribution can lead to safety concerns. Mechanical stability. LiPo batteries might be less mechanically robust than cylindrical or prismatic cells, making them more susceptible to damage from external forces. Connecting multiple lithium-ion battery cells in series increases the total voltage output. We will use an example of 192 cells to see how their individual voltages add up to a higher voltage. The lithium-ion battery comprises 192 cells connected in series, resulting in a total voltage of 691.2 volts, with each cell providing 3.6 volts. We will now look at the advantages of lithium-ion batteries. These batteries have high energy density, meaning they pack more power at a lighter weight than other battery technologies. They perform well at high temperatures, making them suitable for various environments. They experience minimal self-discharge, so they hold their charge for more extended periods when not in use. Individual lithium-ion cells provide a nominal voltage of 3.6 volts, which is convenient for powering many applications. Let us now look at some of the limitations of lithium-ion batteries. Lithium metal is reactive, raising safety concerns if not handled properly. Early lithium-ion battery designs were prone to overheating and thermal runaway, a dangerous chain reaction. Overheating can still occur in some lithium-ion batteries. In extreme cases, overheating can lead to explosions. Let us look at our lesson summary on lithium-ion batteries. These batteries power modern BEVs due to their high voltage, energy density, long lifespan, and low self-discharge, with each cell typically delivering 3.6 volts. Each lithium-ion cell contains a positive electrode, lithium metal oxide, a negative electrode, usually graphite, and a lithium salt electrolyte, all separated by a porous membrane. Cylindrical cells offer excellent thermal management and mechanical strength. Prismatic cells deliver higher energy density. Pouch cells provide design flexibility with thinner profiles. Lithium-ion battery packs are made of multiple cells connected in series to achieve higher voltages. For example, 192 cells can provide 691.2 volts. Despite their advantages, lithium-ion batteries have limitations such as potential for overheating, structural vulnerabilities, and complex thermal management requirements. Thank you.